Okay, so for the first part of the question, we're asked to graph the Vout1 waveform from 5.5 to 9.5 milliseconds. And so since that is basically just the input waveform going through the clamp circuit, we look at the voltage gain that we're going to get from that clamp circuit, which is equal to VO1 is equal to VI plus V negative peak minus VD naught, which is going to give us a 6-volt shift in every single value from the original input waveform. And so now for part B, we're asked to graph the VO2 output waveform from 9.5 milliseconds to 13.5 milliseconds. And we can use this by using the equation for an integrator as seen right here. And since the output wave or the input waveform VO1 can be represented by 5 areas under its graph, A, B, C, D, and E, which is represented by this quantity right here, which is equal to the integral of the input waveform from those respective time periods. And then the negative 10 multiplied by that value is equal to the 1 over negative 100 milliseconds. And then when we also add the previous initial condition, which starts at V out 0 according to the instructions, we end up with these 5 values for our VO2 graph, which graphed here pretty much leads to a negative ramp gain or integrated value over VO2 because A, C, and E are large positive values under the graph, which are inverted or integrated and inverted, which is why it's scaling downwards. And then it has these tiny humps for this area and this area right here because that represents the inverted negative area under B and D from the original output waveform from 10 to 11 and 12 to 13 milliseconds, which is why it ramps up. So in part C, what we're asked to do is we're asked how many pulses are required from VO1 to create that 10 volts absolute voltage shift. And what we can do is we take these two equations right here that when added together represent the total voltage shift per pulse in the original input function, which is VO1, which is 0.093 volts. And to solve for how many pulses that's going to take to equal 10 volts, we pretty much just divide 10 by that value to get the number of pulses, which if we ignore the first bit from 9.5 to 10, since it's considered negligible, we can pretty much assume that it's going to be about 107.5 to 108 pulses, ignoring that first part. So for part D, what we're asked to do is we're asked to qualitatively explain how VL1 changes if R1 is not large enough. So basically what's going to happen here is that the resistor in the integrator is pretty much equal to a load for the first part of the circuit for the stage 1 clamp. And so what's going to happen is that when the capacitor is no longer charging up from the diode after those 2 milliseconds, R1 is going to act as a load. So if R1 isn't large, what's going to happen is we're going to have a lot of current flowing through it, which is going to create a lot of voltage drop. So what we want is we want a really large tau value from a very large resistor, which is going to make it so that the capacitor takes a long time to charge and discharge, which is going to result in us maintaining our shift from our clamp capacitor so that we maintain that positive 6 shift in our VO1. And because if R1 isn't large enough, then what it's going to do is we're going to leak voltage from that clamp capacitor and we're going to slowly lose our shift in VO1. And we're going to know if that value is big enough, however, if we compare our tau value to our input waveform period, which is 2 milliseconds. So if our tau is significantly larger than our input waveform period, then we know we're going to be fine, and tau is going to be large enough so that we can ignore the loading factor.